Am I mic'd up effectively? Am I mic'd up effectively? A show of thumbs if you can hear my mic'd up effectively. There we go. Excellent. Lovely and wonderful to see all of you here in Greece. Hold on. Yassou Athena. There you go. Thank you. Thank you. There you go. All right. There we go. That was less than impressive, I know. So, what are we going to cover today? Code that moves the world, the rise of physical artificial intelligence. Software is no longer eating the world. Many of you will have heard this phrase from Mark Andreessen, lest he be forgotten. It is now, in fact, building the physical world. So, a very brief overview of me. There's my love of the physical world from a young age. I run a company called Standard Matter that deploys physical AI infrastructure based at South Park Commons in San Francisco, in Silicon Valley. And I also run a company called Codesmith that trains AI and software engineering talent. Maybe our largest client is the United States Treasury, where we're their AI workforce partner. And we are Forbes' #1 AI training program. And I also work at Oxford on robotics and ML, and creator of the Hard Part series that probably 2 of you have seen. Yep, 2. Okay, excellent. So, what are we going to see today? What has happened to physical AI in the last 24 months? How did this happen? What is this physical AI look like? What is the architecture, the system architecture behind it? And as software engineers from a whole diverse range of backgrounds in the room, can we in fact actually even be part of this transformative revolution? It would be quite sad if at the end of this talk we concluded that we could not. So, what's happened in the last 24 months? Robots have got profoundly more intelligent. This is physical intelligence, a company we'll talk about a lot today, a research-led company led by Chelsea Finn at Stanford and by Sergey Levin at Berkeley, and their work is really remarkable. But among many, they are allowing us to have robots follow human instructions, human language instructions. Here, we have our robot arm, following the instruction, cut the zucchini, cook the sweet potato. And it can deal with changing environments, even if it's not seen that zucchini shape before, or it's not seen, or courgette shape before, or it's not seen that sweet potato before, or it's not seen that time of day, that lighting pattern. It's in a slightly different position, the cutting board's in a different position. It can deal with it. This is remarkable. This is intelligence, the ability to deal with novel situations semi or fully autonomously. And they're showing emergent capabilities. Just last week, Physical Intelligence's new foundation model, 0.7, was released. And we can see here in the video, it never saw this slow cooker before. And yet somehow it knew how to begin to interact with it to open the drawer. Our robots are becoming intelligent. Just like our language models allowed us to deal with novel situations and have some sense of intelligence, we're now starting to see that in the physical world. And our robots are starting to look really interesting. Some very cute, like this adorable Ricci Mini from the wonderful Hugging Face, based here, Le Robot, based here in Europe, based in Paris. Some very cute, and some incredibly creepy. Look at that. One for you, one for your partner. Ready to fold you up. Put you in the laundry basket. Yeah. New form factors. And they're becoming more human-like. Here's our lineup of some of the most breakthrough humanoid robots. One from Sunday here, Agility. This one's for industrial settings in factories. We've got Neo, a European-based one, with the soft fabric, very strange. G1 from Unitree. This is our go-to off-the-shelf. Buy it, get it delivered on Amazon. We've got our Agile, that's another European one, based in Germany. Figure 03, and our incredibly cute Sprout from Fauna Robotics, very cute. And, as I say, becoming more human-like, the good, there we have on the left, adept running, trips over, keeps moving. The one that needs work, I didn't include, I'm sure you all saw this video. Very interesting that I didn't include the actual moment because I don't think it's appropriate to show our poor humanoid friend. But there it is on its stretcher. And that does, by the way, of course, raise the question, people, when we see these humanoids, what is the emotional attachment we're forming to them that I don't want to show the moment when our poor humanoid has its fall? But this is where it gets really interesting. From experiment and demo to moving into actual industry, workplaces, and our homes. This is remarkable. Automating and scaling lab testing. There on the left. Medra here, just a remarkable scalability of lab testing previously unattainable. Welding robots for those tight or highly dangerous conditions. And then here's our lovely Sunday robotics memo, making coffee at home with everybody's favorite, Breville. Is that the brand here? I don't know. Coffee maker. There it is. They're entering real-world environments. We may just be beginning, but it's happening fast. Why? Well, in part, because there's billions and billions being invested in this space. My personal favorite, physical intelligence up there, just took another $1 billion of investment. They are very research-led, doing a lot of the groundbreaking work. Bezos just swooped in and has raised already nearly $10 billion for a brand new frontier AI lab. It ain't for LLMs, it's for physical AI, known as Project Prometheus. Over here, Hadrian, worth $1.5 billion, is automating entire factories, creating what's called dark factories, end-to-end automated. And then over here, hanging out with Jensen, we have the agility robotics, industrial humanoid. They've also raised vast amounts of money to automate our manufacturing. This, people, is physical AI. Intelligence that can sense and understand our world and then take action within it. It's robots, but it's also drones, it's also factory machinery, it's also autonomous vehicles. And it looks so different. It looks so different, people, to just 24 months ago. There were remarkable things being achieved. Take a look at this top right here. This is what's called a lighthouse factory based in Tennessee from LG. Really remarkable achievement. And then, of course, our dancing Boston Dynamics robots here. I always find that one in the middle extremely, personally find them very, very odd, very creepy. But these, nevertheless, despite being remarkable, are actually not what you would think of as intelligent. They're running in tight, literally often steel cages because they cannot deal with generalized problems. You bump them, they stop working. These are not the sorts of robots you're going to have in your home, in your workplace, or really in more open-ended industrial settings. And they're entirely deterministically pre-programmed. That is to say, that Boston Dynamics demo, while very fun, every step there was calculated using things like inverse kinematics, PID control, using proportional, integral, and derivative terms, and yes, some advanced techniques, model predictive control, but this was where we were at. This was not robots or intelligent beings able to interact in novel settings, deal with new scenarios, and plan accordingly. This was an old world of robotics. So, what changed? What changed, people? 3 things. 1, hardware. 2, data. And 3, of course, artificial intelligence. So, starting with hardware. Here it is. In the old days, we had to manually put together, maybe custom mill, certainly custom access, custom design our actuators. That might be our gripper, the hand. That might be our arm. That might be the sensors. And then we have to build out rigs costing hundreds of thousands of dollars from scratch, customized every flipping time. Now, we have the ability to get off-the-shelf sensors. Okay, that maybe isn't so remarkable. Actuators, arms, grippers, but even literally full humanoids off the shelf, off Amazon, particularly thanks to Unitree and Fourier, both Chinese robotics companies. Even at the low end, we have, again, the remarkable and wonderful robot ecosystem, shout out to France, shout out to Paris, and Seed Studio that provides a lot of their hardware. And a lot of this came, people, from the mature supply chains that emerged from our phone manufacturing process over the last 20 years, and increasingly from the autonomous vehicle deployment. Many of you have, well, I hope, maybe not, gone into Waymo. This scaling of the manufacturing of LiDAR sensors, of the components of autonomy, is what's making this very possible. And then finally, we have a breakthrough in edge compute, the ability to do this work actually on the hardware itself. Things like NVIDIA's Jetson, Thor, that allows us to, with a far lower power draw, nevertheless do hard inference that goes into the intelligence layer. 2, our supply of data on robotics is exploding. This is the second reason why things have shifted so dramatically in the last 2 years. Now, this data comes from a range of places. Some of it is traditional data sets at scale, actually from the web. The very first source of data is our WebLI dataset and earlier versions that give us data on what is happening in an image. I can have a picture, it's a strawberry, and I have the dataset that can inform a model that can map that description, strawberry, to the position in the image. I'm starting with that sort of dataset to get an understanding of the physical world, of what's going on in it, images of the physical world only. OpenX embodiment data, this is a cross-institutional data set developed collecting vast amount of robotic video, and we'll see in a second something called proprioception, that's the robot state and position data. The robots data platform from Hugging Face, also where we can upload our own robot video data. And then teleop data. This is a core part of how we collect data to, we'll see in a second, do something with AI. Teleop data can even be achieved for as low as $100 or less, $100 or less, with our SO101s, again from good old the robot. These are where I have a leader arm and a follower arm, leader gripper and a follower gripper, and I can move manually the leader arm. My follower arm directly mirrors it, imitates it, and I can then record that arm doing the task that I'm leading on, and now I have some training data that I can use for something we'll see in a second. But it's not enough. This stuff is profoundly costly to produce. That's why there's billions going into it. So we also have our simulation or synthesized data. This is the other key part of what's accelerated this transformation in the last 2 years. Our synthesized simulation data. Where do we get it from? Well, sim-to-real tools like the one from NVIDIA, Isaac Sim, or Mujoko, multi-joint dynamics with contact. There we go. If anyone wants to know the acronyms. Allows us to spin up, change the background, even change the physics properties, change the environment, change the end effector. That's the bit that's actually doing the work on the robot. In sim, many, many thousands more times and faster than we could ever do in reality. But they're limited, and that's where world models come in. A new breakthrough area, also with a huge amount of investment. Can we actually build simulated environments that truly emulate the physical world? And there's one by Fei-Fei Li, who runs World Labs, Fei-Fei Li, one of the godparents of AI, who runs World Labs, the Marble platform that allows us to spin up simulated environments that really aim to represent the physical properties of the real world. Okay, but of course, really, these two only enable the most transformative part in the last 2 years, and that is our AI models. They're what's changed everything. We are switching from traditional move the arm here if you want to pick up the strawberry, recognize the strawberry, move the arm towards it. If you get too close, move back. We're moving from traditional control heuristics to end-to-end learning. Our foundation models switch to prediction. Just like our LLMs take in an input of text and predict the best response, predict the best next token, which might be a subunit of the word. So too here, we're going to take in some data and predict, we're going to see the continuous set of actions that our robot arm should take. Our inputs will be vision, an image stream of what's happening. If the arm is missing the strawberry, the image will know that. The image will capture that. Our language command, pick up the strawberry. And our proprioception, fancy word for the current state of the robot. Its joints, velocity, how fast they're moving, and their exact position. That's our input data. Our output is then going to be a series of commands to the motor for where it needs to move next to achieve the original goal, pick up the strawberry. We're going to see much, much more about this. It means it can even handle long reasoning chains, tidy the kitchen, and it can break it down into subtasks. Pick up the strawberry, put it in the refrigerator. Pick up the strawberry, go to the refrigerator, open the refrigerator, put the strawberry in, close the refrigerator. Cross-embodiment. This is going to allow us to actually apply this AI model not just to an arm with 5 fingers, but a gripper with 4, or 2 arms, without profound amounts of fine-tuning of the model, because it's learned to understand and reason about physical space in a more general sense. And emergent capabilities. This gives our robots, our AI models that are driving them, the ability to take on novel challenges, like opening a brand new appliance that they've not seen before. These are our 3 key changes in the last 24 to 36 months. What changed? Hardware got great and cheap and faster to get. Data got collected. We're still collecting a lot of it, but it got a lot more collected. And AI got to predicting stuff, not deterministic, do this, then that, if state is this, then move over here, but predictive action trajectories. Go in this direction to achieve the goal. So, let's review, let's lay out how this physical AI system actually works. The layers, from the bare metal up to the AI intelligent model. Walking back and forwards every time. Here is a software engineering view of the physical AI stack. Starting at the bottom there, this is our real-time control. We're dealing with actuators, robot arms, that are doing things and need to do things to stay balanced 1,000 times a second. We're dealing with low-level kernel operations. We're dealing with communication that needs to be low latency, and if there's some network jitter, it's going to break and potentially actively harm the person interacting with the robot. This layer is crucial for real-time relationship between the model's prediction and the actual end effector, the arm, the gripper, the humanoid. But we can't be dealing with that layer, the whole time, directly controlling the kernel. That ain't going to be possible. We need some platform or middleware in between. That middleware is crucial. It includes our hardware abstraction layers, our HAL. It includes our robot operating system that allows us, it gives us the tools, the libraries, the conventions that enable us to build these complex modular robot applications. That is then the bridge to our intelligence layer, the AI models that take in our data and predict the actions that the robot needs to take. All of this is supported by a data and learning loop. Core to any AI model, we collect data from all those different sources I described. Then we train our model on that data so that it can map where the robot currently is to what it needs to do next to complete the task. We then eval it. We assess, is it working? Is it working right? And then we deploy it to the robot, which, by the way, of course, it's now completing tasks, hopefully valuable enough that it's maybe for money, for that economic value, and it's providing more data to then loop back around again. And that's all interacting the whole time with this core stack, the low-level hardware control, the platform and middleware that acts as the integration to the intelligence AI models. So let's explore them in a little bit more detail. So first, real-time control. We started describing it. We're dealing here with bare metal levels of optimization. We're trying to achieve 1,000 updates a second, potentially, at the hardware level. Our actuator, our arm, is going to need to respond at 1,000 a second. We're going to need to have sensors provide updates at that sort of rate. Anything here that is not deterministic, something gets in the way, something is prioritized at the kernel level. Remember, our kernel, people, is that core operating system component that handles low-level communication between our hardware and our software. Anything that gets in the way there could directly cause our robot to fall over, could cause it to harm somebody. Any network jitter, any instability could lead to broken gears, could lead to serious harm. This part is crucial. But we can't be dealing with it directly. So we have our bridge. Our bridge allows us to connect our simulation, our developer tools in, our telemetry so we can live see what our robot's doing, our hardware and our models. It acts as the bridge to the really profound breakthrough layer. Those other two, they've been around for a while. What's really transformed the AI physical stack in the last 24 months is our core visual language action or similar models. Here's our core AI model. What happens? Our core AI model's goal is to enable us to map where our robot currently is in terms of its goals into the next steps it needs to take to achieve those goals. What's our input data? Well, we've started to describe it. It's what the robot's currently seeing and what we're currently seeing of it. A video stream of the robot trying to complete the task. It's our instructions, pick up the strawberry. And it's our proprioception data, exactly where is the arm, where are the joints, and how fast are they moving. During our training stage of this model, our goal is to take that information, and because we have a lot of recordings of the task being completed successfully, map the current state to what were the successful actions that were taken next that completed the task. See enough of those, and we have a map. We have caught the pattern. We can then, for new tasks, picking up the strawberry where it's in a different position, picking up the strawberry where the light is bouncing off it in a different way, we can infer, make a best prediction of what the action trajectory, the continuous flow of next steps that the robot should make are. That's our core AI model. And it allows us to do long horizon planning. We can break out our complex set of tasks into individual steps. We've described it. What's this give us, people? This gives us zero-shot generalization. This is the ability to take on new tasks without having to specify how to do it, because our model has learned the universal nature, or at least push towards it, of physical space and how we interact with it. We don't need to explicitly define individual tasks. We don't need to talk about how to move the arm by coordinate to its exact location. And we don't even need to have labeled all of our data. We may have shown it a video of it pick up a strawberry and learned the patterns involved in picking up a strawberry, but now we say pick up a banana because of its underlying understanding, semantic understanding of bananas, strawberries, and pick up, much of it from its information from web text and images, it can pick up the banana. This is a remarkable breakthrough and the core part of the brain of the new physical AI stack. Finally, our data and learning loop. This is the core to an AI model running successfully. We collect our data from teleop, we talked about it, from simulation, from web scale video and text. We then use that to train our model. Ideally, and we've not yet reached this is what physical intelligence, Google are trying to achieve, DeepMind are trying to achieve, foundation models that will be applicable to any physical environment. We're not quite there yet, so we have to fine-tune them to our particular environment with data specific to our particular problems. Then we eval them, and then we deploy them, and then the cycle continues. This, folk, is our core physical AI stack. Real-time control, a platform and middleware, the low-level real-time control, the integrated platform, the AI models at the top, and then the learning loop running through. If only we could be part of this. If only we could be part of building physical AI. This is a part of my acting class. If only we could be part of building physical AI. What a transformative thing this would be for us. Let's give ourselves a shot and look at some of the roles. I think they're quite intimidating, but let's give ourselves a shot. Okay, we have agility, physical intelligence, Amazon FAR, their frontier AI robotics team, and Neura, a German-based robotics company. These are all robotics software engineer roles. Let's map into our areas. Intelligence and behavior, that's the agility senior robotics software engineer. Our frontier AI robotics role at Amazon is on the platform middleware piece. Physical intelligence, the robotics software engineer, that's on our low-level real-time control. And then we've got our Neura role. It's also a robotics role, but it's on the AI data engineer section. Let's take a look at these roles, people, and see if we know what we can do here. All right, look at these. Physical intelligences. This is intimidating. Make perception and control loops work at real-time speeds. Optimize every layer from OS camera pipeline. Underpin our physical intelligence model. Flippin' heck. Frontier AI robotics at Amazon. Design, implements software, diverse AI robotics hardware, autonomous teleoperation. We're not just advancing robotics, we're re-engineering it from the ground up. I hope everyone can tell they AI generated that job description. You'll develop, here you go, Neuras, you'll develop the cognitive abilities of our robots, push technical boundaries, shape the future of human-machine interaction. And agilities here, expand and generalize our humanoids, robots, real-world capabilities, design complex behavior systems. People, I'm worried, with all these intimidating roles, it's such a shame we can't be part of it. I'm not sure we've been part of the internship. Here's robot software engineering internship at Agility. Robot behaviors, robust, reliable, behavior planning, software integration. Raise your hand. That's lame. Raise your hand if you feel hopeless. Okay, good, all right. Yeah, very good, very good. But it turns out, people, we can very much be part of this revolutionary moment. In fact, 80% of software engineering for physical AI is what you all do, we all do as software engineers every single day. The first bit is our good old core software engineering and architectural work, system design work. It's CI/CD, it's deployment, it's maintainable code bases, it's full dev lifecycle ownership. Look at these actual bullets for the requirements of those JDs, those job descriptions, those roles I just mentioned. 5 years of full software development lifecycle, coding standards, build processes, strong skills in C++, Rust or Python, optimizing production software. In fact, not one of those roles has any requirement that you must have specifically robotics experience or degree. They might mention autonomy, but we'll see in a second, you might have more experience in that than you think, at least after the last year or two. So let's look at some case studies. What are they actually doing at these companies? Agility here. What's agility actually doing? Agility robotics are manufacturing industrial automators. What are they actually doing? They're building a maintainable robot software framework. Feel familiar? Maintainable software framework. They proudly announced, Chris Paxton here, at a great seminar worth watching, he's their head of AI, proudly announced they've scaled their internal software stack. That's their core achievement. What are our key insights for us? The major challenge to get this stuff from demo to production is, of course, engineering reliable, evolvable software platforms that turn the breakthroughs into actual deployable fleets of robots. Feel familiar? Treat robot software like any large distributed system. That means your good old, well-designed abstractions for other engineers to pick up, easy understanding of what's going on, your logging, and then long-term maintainability of your code base. It's not the demos, it's the platforms that are going to create the winners. We know it, we love it. There is another part that's very, very typical. You may not all have done it, but it's your low-level software engineering. Not everyone in this room will have done it, but many of you will. It's also familiar. We've talked already about how important that low-level work is for robotics. Performance tuning, trying to control we want our models to be non-deterministic. We want our models to deal with new scenarios based on probability, but we do not want our low-level control to be non-deterministic. That's the balance of the robot. That's the robot falling over. So there, we want to be able to handle directly our memory allocation. We want to directly patch or interact with our kernel. We want to control, we may want to bypass our kernel, access the socket directly. These are all things that are in this job description from physical intelligence and from Neura. And what's NVIDIA doing? NVIDIA is doing just that. They're giving control, preemptive control to the kernel in real time with their software to guarantee deterministic, ultra-low latency execution of control loops. What's the lesson for all of us as software engineers working in physical AI? Well, it looks like guaranteeing predictable real-time behavior is what matters to transform the AI layer, the predictions, to actual real-time impact in the robot. Feels very much like anybody in this room who's done any systems engineering, any performance engineering. What else is part of that 80% that we've all done day in, day out? Regular old platform engineering. Anyone in the room who spent time working with distributed systems, with cloud architectures, integrating complex systems, different hardware, different teams, and creating, nevertheless, reliable tooling and testing for those systems. All of these JDs work with hardware engineers to integrate optimized pipelines, design, build frameworks to accelerate development across applications. Let's see what Agile in Germany is doing. What are they actually doing? Cloud platform for humanoid fleets. That's what they're most proud of right now. Quite right too. An AI-powered software platform that connects heterogeneous robots, mobile robots, PLCs, that's our very traditional factory components, manufacturing components, such that they can do things like continuous updates, share intelligence among them. That's your platform engineering, people. You know it and you love it. All of this is what makes actual factory-wide. No factory has one robot. No factory has one PLC. They're all integrating multiple different providers at the same time. You actually want to make manufacturing transformative, you're going to need to have very much the same evolvable stack that's going to enable you to move from isolated robots to full production scale physical AI. Don't worry, people, there's more that you're already good at. Two more. One more, good old data engineering and pipelines. You're so good at all this stuff. Good old data engineering and pipelines, also very familiar to everyone in the room. Extract, transform, and load your data. Ingestion, data set curation, quality of the data, inference, scaling of that data. automation, good old governance and security and ops of the data, data management and processing. These are all classic parts of data engineering, and when data is the fuel of physical AI, you can imagine it's a very central part. All these jobs here, the newer robotics one in Germany, build optimized data models for robot applications, ensure governance, security, quality across all platforms. Let's look at their actual training facilities and platform. They actually build large-scale physical gyms where their robots can practice tasks. And then they do that massive data pipeline to collect all of that multimodal data, video, tactile sensor, etc. What's our lesson? Actually integrating these large-scale data sources into well-managed pipelines is what turns live operations into data that can iteratively improve our core models and deployment. This is absolutely core to physical AI. And finally, the one that I'm sure was not familiar to all of us 2 years ago, but now for many of us will be familiar, is integrating AI models and agents into production settings. This is crucial. Breaking down complex tasks into individual stages. Control flow, handling failures. We all know this if we've ever integrated an agent either into Claude or into our own, or into a production workflow. We're all very familiar with this. You can see it all here. You'll be the person who makes AI models run flawlessly in production, says physical intelligence. These are from those JDs I just showed you that sounded so intimidating. They're all the good stuff you know. Covariant, now at Amazon, now being bought or integrated into Amazon. Let's look at their new foundation model, RFM1, generalizable agent-like intelligence for warehouse robots. They shifted to goal decomposition, dynamic reasoning, and autonomous failure recovery. That's your agentic engineering stuff that you're doing every day. Trained on, next one requires hierarchical model integration. Every time you've thought, I'll have a high-level planner agent model that then delegates tasks to other models that maybe are cheaper or more task-specific. Maybe they've been fine-tuned to handle another task more cheaply. That's this, hierarchical model integration. You know it, and you love it. So, these are all things, people, that you can be part of. 80% of this revolution is stuff you already know. Core software engineering and architecture, low-level system engineering, platform development, data engineering and pipelines, and integrating AI models and agents. So, what the heck is actually new? What is new in physical AI? 3 things, and they're really important. But they're 20%. They're really important, though. 1, speed. 2, physics. And 3, data. So, let's look at speed first. As we've said, in physical AI, it is absolutely crucial. The physical world is brutal. The latency we need to achieve is absolutely minimal. We're not as focused on throughput, we're focused on predictability and speed. Even 20 milliseconds of latency could cause the robot to cause harm. So controlling the flow of tasks at the kernel level is crucial. And foundation models have to think about this too. And there's lots of techniques. Foundation models aren't necessarily generating outputs, tokens, at the rate required. Our foundation vision, language, action, or robotics models aren't predicting what to do next fast enough. So what do? Well, I'm just going to show you one example of a technique here called action chunking with transformers. It acknowledges that the core reasoning model that understands what's in the image, understands there's a strawberry there, understands the robot arm is a bit too far away right now, understands that the position of the robot at this point is not close enough to pick up the strawberry. It's only going to predict 1 token at a time and maybe only make 10 predictions a second, then we're going to have a jittery robot. So we have action chunking with transformers, where we predict instead a whole continuous trajectory, 50 actions at once. And then we do it again, giving us smooth movement. Now you might be like, well, hold on, what if new information happens in between? We knock the robot, it bumps. We can use a sliding window. And these are the kind of edge case techniques that are being refined in these models right now. Every release, every month, a new model optimizes for this. It's crucial. What else is new? Physics. We are now writing code, deploying models that are interacting with the messy, rules-based, but highly dynamic physical world. We've got noisy sensors, we've got gravity, we've got momentum, we've got contact force, we've got tactile feedback, the smoothness, the roughness, the friction of the item. Ultimately, perceiving stuff, as a robot does, and then manipulating the world in response is a physical thing. There's no getting away from it. With all the physical bearings of that, we need new techniques to deal with that. I want to show you just one here, just to give you a hint, because this is the area that you want to go and explore. Vision-based tactile sensing. This is absolutely extraordinary. And by the way, cheap at this point. Digit and GelSight make these cheap. What's this do? This allows our gripper, our arm, our hand, our robot hand, as it picks up the egg, it puts some small pressure on it. We have inside our vision-based tactile sensors, we have little internal cameras that capture gel pad deformation. That's the gel pad being compressed, and they're capturing the change of the shape. That allows us then to build high-resolution touch maps of that interaction and use that data to inform our model's prediction so it doesn't drop the egg. It doesn't slip out of its gripper. But fundamentally, physics is dynamic, unforgiving, and it requires us to think our code, our sensors, and our models, rethink them in a way that captures that dynamic system. And finally, data. If we thought we needed a lot of data for large language models, we don't know how much data we're going to need to model and capture the details and anomalies of the physical world, the multimodality of the physical world. To train capable robots, an extraordinary amount of high-quality data. We have 4 main buckets to do so: the teleoperated, the real world. Once that robot's deployed, that's new training data as it does its task. Our massive synthetic data, including the world models we started to describe, and reinforcement learning rollouts. These are used a lot in autonomous vehicles as well. Here's one from Google, Genie 3. It's a world model that you can describe a scenario, and it builds it, and is it an interactive world. That allows you to simulate your robot in environments that are hopefully highly sophisticated. They're getting more and more so, and that provides legitimate synthetic data for our training of our models. These are our big 3 new parts of being in physical AI. It expands traditional software engineering with speed so that our robot can safely handle the real-time demands of the physical world. With physics, the forces of the demanding physical world are messy and complex, so we need data that is grounded in that reality at an unprecedented scale. Where do you begin? Well, you take the parts you know, the 80%, and then you add in these new parts of speed, physics, and large-scale data to build your first physical AI project end-to-end. And here it is. And this is well within everybody in this room's abilities. You use SO101s, maybe Le Kiwi, both from the robot, of course, to train a policy. That's a model that's tailored to your particular situation that will, here's an example, close your laptop lid. You'll grab it and close it. There's the cute S1, the very uncute SO101s, one of the least cute. I put a little Lego unicorn head on the end of mine so it's less threatening. It's going to close your laptop based on some trigger. The trigger might be you've been on social media too long. The trigger might be it's midnight. The trigger might be, I don't know, whatever your trigger is that means our laptop lid needs to close. What do we do? How do we start? Well, first we got to collect data. I already mentioned with our SO101s, we're going to have our leader arm and our follower arm. We're going to, with our leader arm, teleoperate our follower arm to close the laptop lid. We're going to record what's called episodes. They're individual runs or recordings of that training. We're going to do maybe only 50 times. We're going to do it under different scenarios. The laptop lid's here, it's here, it's here. We're going to have different lighting. Maybe the light's on, maybe it's a sunny day, maybe it's a dark day. We're going to have different positions that you, the person, are sitting in. We're maybe going to have slightly different positions of the laptop on the table. We're going to record all of them, teleoperated, doing the actual task, record the video. The robot software will capture the proprioception data at the same time, the exact joint positions and velocities of the robot joints. We're going to save that data, and then we're going to train a policy. We don't need to teach it what a laptop is. We don't need to teach it, other things. It's got that background information from its core foundation model. But we're going to train a policy end-to-end that understands when the laptop position is here and the gripper is here, what is the optimal next set of actions, continuous action trajectory for the gripper to take that most typically led to the laptop successfully closing and the task completing successfully. That's our training of our policy. Then, if we want to test it out under different situations, we open up our simulator. And we run that policy and see how many times did it work. Maybe we try doing some new training runs. And then we deploy it. We put it live directly onto our ISO 101, which, by the way, we can buy for under $100 or 3D print for even less. And then we run it and we generalize it, hopefully even to new situations. But fundamentally, what we do not need to do now is write, if you see laptop screen there, then move arm down. If it's over here, move arm towards it. All we have to write is, if social media too long, then run function, robot close laptop lid. And whatever the setup is, we now have a policy that can handle it. Because our policy has learned how to find the laptop lid end to end from those training examples. It's learned how to plan a smart trajectory that achieves it. It's learned how to control the joints on the arm to achieve it. It's learned how to apply the right force. It's just got to achieve the task. And therefore, it's learned to close the lid. So, your next hello world can now be an arm reaching out, understanding its environment, and then acting on that environment because of code that you all wrote. The physical world is just a new platform for us as software engineers. So now go write code that moves it. That's it, people. I'm happy to answer any questions. If people want to stay to ask questions, I'm happy to stand up here, answer any questions. But thank you, everybody. It's lovely to meet all of you. And yeah, come ask questions if you have them.
Thank you, Will. Thanks.